Good evening. Good evening. My lords, ladies and gentlemen, thank you for joining the Rank Prize Funds this evening for the 25th presentation of prizes. And I'm very grateful and welcome Lord Darcy for joining us here tonight and kindly agreeing to present the prizes. It is rather humbling and wonderful to see how the legacy of Lord Rank, my grandfather's vision, has developed. He set up the prizes in 1972 to support research into two areas of science that had supported his businesses, recognising without research and development, his businesses would not have thrived. He had lived through an age where movie films had been created, transitioned to sound, and then into colour. I think you'd be amazed by the advances since 72 in science that have occurred, and I'm only sad that he could not be here now to see how applicable his vision was and how well his legacy has been used in this endowment. The pace of scientific discovery continues to expand exponentially, so we're incredibly fortunate to have two outstanding committees in these two fields. Through their diligent and well-judged application of these funds, both in supporting research and in recognising the impact of the and application of that research, excuse me, I believe our work remains current, hugely relevant, and supportive of scientific research, the scientific research community. Symposias remain at the core of our activities, and since we last gathered to award prizes, have ranged from parallels between acoustic and EM electromagnetic radiation in the structured materials and fibre optic and photonic sensors for industrial and healthcare in the field of optoelectronics. It has been equally wide-ranging in nutrition, from malnutrition through the life courses to new crop protection. So I'd like to say a huge debt of thanks to Donald Bradley and John Mathers and their subcommittees for their ongoing commitment to the fund's work and inspired selection for the 2020 prizes. It is also important to recognise that the fund's activities have helped build global informal and formal networks that encourage cross-pollination of ideas and encourage support to young scientists, from gatherings at the symposia to vacation studentships and the Rank lectures. I'm hugely pleased to welcome back tonight over 10 prize winners to this 2020 prize giving. It is a testament of the importance to our work that the network developed around the world that we can persuade so many eminent scientists to join us on what is a rather wet and sometimes cold winter's day. It was also wonderful to extend our congratulations to Professor Arthur Ashkin in 2019, who won a Nobel Prize for his invention of laser tweezers, work for which his colleague, Professor Joseph Dzierżyk, and he were awarded the Rank Prize Fund for Optoelectronics way back in 1993, so we still like to feel we lead the field in our selection of prize winners. None of the legacy of the Rank Prize Funds would have happened without the support and guidance of the trustees and the Prize Funds home team. It has been a period of significant change for the executive team, so I'm hugely grateful for the hard work of Karen Bucklow in assimilating the broad range of the fund's activity in the last 18 months, and for managing seamlessly to take on the baton of the Prize Fund's work, and with her, Colleen Gray, who tonight has successfully laid on this evening's prize ceremony. I'm immensely grateful for Lord Darcy in carving out time in his hugely busy diary and joining us to present the prizes tonight. Pure science and its research and its application have always been vital for any nation, but being able to then engage and weave into this national policy and ensure that politicians understand the importance and the implications of that science is both a huge skill and a significant altruistic personal commitment. So we are hugely fortunate to have Lord Darcy join us this evening and to present the three eminent scientists their prizes. The list of his work and research is wide, and I won't dwell on it too much now, and the list of establishments that he has worked with and the recognition that it has received. Whilst his work is most recognised in surgery through robotics and minimal invasive surgery, I'd like to draw attention to his research in medical imaging computing and its links to optoelectronics, and his policy work, amongst it the London Health Commission that reported on health and well-being and obesity emergency facing London's population in 2014. This wide-ranging work was highlighted in his nomination to the Royal Society. I have a huge respect for how you've embraced and bridged both optoelectronics and nutrition in your work. I've had the privilege of chairing these funds for 4 years, but I'm yet to find a way of bringing the optoelectronics and nutrition committees together in one symposium. So at dinner tonight, I'm going to quiz you on how you can do that bridge. But firstly, I'd like to call on Professor John Mathers to introduce our prize winner and the citation for nutrition. John.
The Rank Prize for Nutrition is awarded to Professor Sir Stephen O'Reilly for his outstanding research that has advanced understanding of genetic causes of obesity and its treatment. Professor O'Reilly has made seminal contributions to understanding genetic causes of obesity in children that has led to novel treatments, more effective approaches to diagnosis, and information for families that can help them deal with severe obesity in childhood. His pioneering work has shown that defects in specific genes which regulate human energy balance are causes of both rare and more common forms of severe obesity in children. Contrary to prevailing dogma, O'Reilly showed that these genes were important in controlling appetite, and that when absent or defective, cause severe overeating. In particular, the discovery of defects in a gene encoding an appetite-suppressing hormone leptin was paradigm shifting. Prior to this, most severe cases of childhood obesity had been thought to be caused by failure in energy expenditure, low metabolism, rather than excess energy intake. Leptin was first discovered in 1994 in an obese strain of mice, obob mice, as a hormone produced by adipose tissue, fatty tissue, and which suppresses eating behavior. Absence of the hormone in mice was found to be due to a mutation in the gene for leptin, which causes the affected animals to overeat, leading to extreme obesity. Although leptin was soon found to be produced in human fat depots and appeared to have the same function in controlling energy balance, early studies showed that the gene defects found in mice were not observed in their studies of patients with obesity. However, O'Reilly's clinical genetics approach, which involved studying extreme, rare forms of childhood obesity, proved to be the solution to this conundrum. Within 3 years of the discovery of leptin in mice, he had demonstrated the first mutations in leptin in severely obese children and started treating them in his clinic using recombinant leptin. Dramatic responses to this treatment were observed, with replacement leptin normalizing not only body weight, but also reproductive development and immune function in these children. In 1997, in addition to his discovery of human LEP mutations, O'Reilly's laboratory reported that mutations in the neuroendocrine-specific pro-protein convertase, PCSK1, could also lead to severe obesity. Together, these findings established that human beings could become markedly obese from a young age due to disruptions in single genes. He and his colleagues went on to discover mutations in several other genes, including, simultaneously with the laboratory of Frogel, MC4R mutations, which are found in 5 to 7% of severely obese children. Importantly, through detailed phenotyping of affected individuals, O'Reilly's group demonstrated that the principal driver of obesity in these cases was a failure of control of appetite. O'Reilly's laboratory collaborated with others in defining the genetic basis for common forms of metabolic disorders related to obesity, most notably in work undertaken with the MRC Epidemiology Unit and his close colleague David Savage. O'Reilly found that the major genetic basis for the propensity to develop insulin resistance and the metabolic syndrome major risk factors for type 2 diabetes and for cardiovascular disease, under conditions of excessive energy intake, lay in the inability to expand safe fat storage depots on the hips and thighs, rather than any specific pathogenic role for central fat. The Rank Prize recognises Professor Sir Stephen O'Reilly's outstanding contribution to both the understanding of the metabolic and molecular bases of rare and common forms of obesity, as well as translation of these findings into more effective clinical practice in children with severe obesity.
Chairman, Lord Wakeham, ladies and gentlemen, it's an enormous pleasure and privilege to be here. To be here and to receive this highly prestigious award. I must admit, I have had great fun dealing with the nutrition community in the last few years. I've even chaired the UK Nutrition Research panel, but I'm not a nutritionist, and I think it's incredibly broad-minded of the panel to embrace me in this way and give me this prize, and I'm very moved by the decision of the panel to do so. This is where I work, at the Institute of Metabolic Science in Cambridge, and there for quite a long time, and before this building was opened, I broadly have been asking two questions. The first question is, why are some people fat and some people thin? And the second question is, when you get fat, why do you get sick? And I wanted to understand those two questions and then use that information to improve diagnosis, prevention and therapy of these overnutrition-related diseases. And in the short time I have today, I'm going to do a whistle-stop tour through a bit of what we've been doing over the last 25 years or so. So, I've used a lot of genetics in my work, and you might think that's weird because actually obesity has become much more common in the last 20 years, clearly driven by environmental factors. So what on earth has genetics got to do with obesity? Obesity is clearly driven by the major environmental changes. Sometimes even people think, I've heard it said, that obesity is a new disease. Well, actually, obesity is not a new disease. It's pretty inconceivable that the Paleolithic sculpture of this limestone figure, some 20,000 years BC, could have done so simply out of imagination. And Hippocrates himself was greatly troubled by how he should manage his obese patients. He thought they should eat once a day, sleep on a hard bed, and walk naked as long as possible. Sadly, obesity management hasn't improved a great deal since then. Daniel Lambert was the jailer in the Leicester jail in the 18th century, the biggest man in Britain at the time, and around the same time a British physician opined that no age has seen more instances of corpulency than our own. So we're not new, although we have become much more common in terms of obesity. And why have it become more common? Well, briefly, I'll tell you it's because we're eating more and moving less. And never have the factors involved in both of those things ever been so prevalent. And I don't think we need anything much more sophisticated than the drivers that have happened over the last 50 years or so for both of those sides of the equation to explain the increased prevalence of obesity. Of course, there are many other suggested factors: antibiotics, pollutants, antenatal environment, your mother makes you fat, the social environment, your friends make you fat. So there are many potential factors involved. And within our own institute, we have superb researchers studying the environmental aspects of obesity. And we do not ignore them, but my own research has been much more to do with the individual's susceptibility or resistance to those environmental factors. So the real question is, well, okay, why isn't everybody fat? If we live in an obesogenic environment, why isn't everybody fat? Well, one hypothesis is that lean people are just morally superior. They're just better than me. They just make the right choices, and they just, or that they just by random chance happen to live in environments that keep them lean. Alternatively, it could be that people have different susceptibilities to being lean and obese. That could be impervious to biological factors or impervious to environmental factors, or could interact. And you won't be surprised when I say that 25 years of research have shown us that people do have different susceptibilities to being lean or obese, but they are modifiable by environmental factors. The reason I know that genetics is important is that you can't really ignore twin studies. I mean, they're old-fashioned, but these are unbelievable twin studies done from Sweden, where in the 1950s, identical twins were frequently brought up by different parents and didn't know they were separated at birth. So they were Mickey Stunkard was able to follow up identical twins who'd been separated at birth and then studied late into their lives, compared them to identical twins who were not separated at birth and brought up together. And basically had to conclude in the red box here, because the correlation with your identical twin that you've never seen was incredibly tight, and those with your siblings that grew up with was almost zero. So he had to conclude, even as a child psychiatrist who couldn't believe his own data, that the childhood environment had little or no influence, and that the predominant influence on adult mass was the genes that you inherited. And if you don't believe that, or you find that uncomfortable, then just look at the picture down here, where we have sisters born on the same day, but sharing 50% of their genes. And they come as you've got all brothers and sisters, you come in all shapes and sizes, but that's because you share only half of your genes, and half of them you don't share. Here are sisters born on the same day, sharing 100% of their genes. Pretty hard to look at those pictures and say, I don't think genetics is terribly important. it's really quite striking. So we knew that there was strong heritability for body mass index and its distribution, but until the work that we started as a small lab back in the 1990s, no single gene had been found, the disruption of which could lead to severe obesity. And the first came from a patient in my own clinic, who we eventually, after several years of biochemical and genetic detective work, discovered had a disruption in a brain-expressed prohormone convertase gene that disrupted numerous endocrine signaling pathways within the brain. And then, much more obviously, soon after the fat hormone leptin was discovered by Jeff Friedman at Rockefeller, we went straight to look for this in children with severe obesity and found these children, first cousins of Pakistani origin living around Luton, who both were severely hyperphagic, severely food-driven from early in life, and were severely obese. And they too, like the mice I showed on the top, were totally lacking in this adipose-derived hormonal signal coming out from fat tissue. This led us to a very exciting period, and I was joined by some wonderful scientists, including Sadaf Faruqi, Giles Yeo, and Tony Collis, PhD students or postdocs at the time, all of whom have stayed within the Institute and stayed as collaborators and close friends for the last 20 years or more. And together, we've had this exciting journey, and we've discovered many genes. Sadaf has led our program in severe early onset obesity for about the last decade, and together we've discovered maybe 15 or 20 such genetic disorders that lead to severe obesity. So I'm not, you'll be relieved to hear, going to describe each of these to you. I'm going to say two things about them. One is we didn't know where they would work when we found them, but when we found them, we found they were all in the brain, and largely in a part of the brain called the hypothalamus. And secondly, we didn't know what they would do to the children until we studied them. So we brought the children into clinical facility, we studied their food intake and their energy expenditure. We said, why are they fat? And they were clearly fat because they were eating too much. And they were eating too much because they do not get the satiety and appetite appropriate signals that you or I or many people get in relation to food. They had a disruption of these central sensing mechanisms that lead to the sensations that we get of hunger and satiety. And they were very, very abnormal in these children. And of course, it's rare in medicine where you get the tremendous privilege and pleasure of discovering a new disease and then be able to do something about it. And by giving back recombinant leptin to those small number of children we found who lacked it, we could totally reverse every feature of their leptin deficiency, including the non-obese related, the reproductive and the immunological, as John mentioned. And there's no child with congenital leptin deficiency who cannot be totally reversed and given complete normal life. In fact, our first leptin grandchild has appeared. In other words, one of these children has recently had a child, has had a baby, been given leptin through her pregnancy and had a healthy offspring recently. And so there's only about 30 such children in the world being treated, but Sadly, we were aware with our collaborator Philippe Frogel and Sadia Saeed about 60 children around one single Pakistani city who are currently dying of this condition and unable to access therapy because of the challenges of getting medicine into Pakistan. So this is an underserved group of children and it's a lethal condition. These children will die of obesity. They get respiratory compromise and die before they're 20, usually of this condition. Treating with leptin taught us an enormous amount. This is one experiment that couldn't have been done in animals because animals can't speak to us. And so what we did in this case is ask these adolescent children who'd never seen leptin, whether they would sit in an MRI machine and look at pictures of food while we showed them pictures of food, or pictures of other exciting things like footballers or money or cars. When we showed them food, the areas of addiction and reward in the brain, the classical comments, lit up like a beacon, and nothing else lit up those areas. Within 3 days of leptin administration, while they were still massively obese, we had totally normalized the areas of that area of the brain. So here's this little hormone, the cytokine, coming from your adipose tissue, and it's speaking to what you think bits of the brain you're in control of, the really higher parts of your brain, totally changing the neurochemistry and neurobiology of these higher parts of the brain. So this Cartesian idea that there's a dualism between the brain and the body is nonsense. Here is a hormone solely produced in boring tissue fat, talking and influencing every one of you right now. In fact, if I stopped leptin working in every one of you right now, you wouldn't be able to listen because you'd be so hungry, you'd be running out the door to get food. So in every one of you, this little molecule is talking to your brain right now. And without it, as I say, you wouldn't be able to concentrate on anything else. So in summary, of our 20 years or more of human genetics, humans can become obese as a result of mutations in single genes. The expression of those genes is highly enriched in the brain and hypothalamus. The principal mechanism through which the mutations disturb energy balance is through increased appetite and diminished satiety. I haven't showed you data that it's not just rarities here. A lot of people said, oh, it's okay, Steve, you found this stuff in rarity, but that can't be relevant for common disease. In fact, common obesity has exactly the same architecture, just milder. And so this is true across the range of body mass index in this room. These processes are exactly the same, they're just lesser in degree. And the effect size, when we can measure it, it is largely these common genetic influence. The changes in appetite between us are what largely determine our differences in body mass index. And when we can define a deficiency state, replacement therapy is dramatically effective. And not just leptin, but now there are other therapies being developed, which we're looking at in some of the other children with different deficiency states, and there's real promise in further therapeutic developments. So I'm going to move now to when you get obese, why do you get sick? And obesity is really a state of energy intake chronically exceeding energy expenditure. I actually don't like the term obesity. I think it leads to brain freeze in most people. We have a very full of prejudice and full of... It actually is, obesity is just defined as a state of having too much triglycerides in an adipose depot. It's an arbitrary cutoff point. Why are we interested in that? Well, we're interested in it because it's associated with making us sick. And it makes us sick in a number of ways. There are kind of what I call the mechanical and gravitational effects of obesity. Simply the weight effects, narrow throat to breathe in, heaviness on our knees, pressure in the abdomen, pushing acid contents upward. These physical effects of obesity. And that's pretty obvious that it is the obesity that's leading to those. But what about the link with cancer or the link with metabolic disease? Why would having an expanded mass of fat tissue lead to those disorders? In fact, does it lead to those disorders? Is that just a biomarker? Is the fat mass simply a biomarker for something else about being in chronic positive energy balance that leads to these conditions? And so how would we get at that? Well, we thought that we'd get at that from the most sensitive biomarker of being overnourished, and that is high levels of circulating insulin in the absence of diabetes. So when you overnourish someone or you deliberately overfeed people, the first thing you can measure almost is the rising plasma insulin as the body becomes more insulin resistant. And insulin resistance is what I've studied for, again, longer than I've been studying obesity. I've studied insulin resistance. And in one slide, I'll tell you what the last 30 years or 30 years of work is. That when we studied people where insulin didn't work because it didn't signal properly because of mutations in signal transduction pathways, yes, they were hyperinsulinemic, but they didn't have everything that we're interested in. They didn't have fat in their liver. They didn't have high triglycerides. They didn't have low HDL. It didn't look at... So it kind of concluded to us that actually insulin signaling isn't really at the bottom of insulin resistance. On the other hand, there was a group of people we studied who looked like everything we measured was exactly what you'd find in obesity. And they were people who had lipodystrophy. That is a condition where you cannot develop fat cells properly, or you can't make triglyceride in fat cells. So it's a primary disorder of fat cell production, or fat cell synthesis of triglyceride. And indeed, we've discovered many of the genetic features of the condition, and we found some mutations in some genes that are only expressed in adipose tissue. And even in those ones, subtle, tiny mutations cause every feature of the metabolic syndrome, including the end stage, including the diabetes, the heart attacks, the hepatoma, the liver cancer, everything, simply due to a disorder in adipose tissue. That really drew attention to fat cell health as a key determinant of systemic metabolic, and that's been recently confirmed in collaborative work we've done with my colleague Nick Wareham and other colleagues in the MRC epidemiology unit. So briefly, these are people with examples of people with lipodystrophy. To you, they may look thin. They're not thin, because no matter how much food we give them, they would never put on fat because they can't make fat cells. And tragically, they are not well. They all develop severe metabolic disease, diabetes, fatty liver, all heart attacks, liver cancers, very early in life. So it's a very serious condition to have, not being able to have enough fat cells. And working with my colleagues David Savage and Inez Barroso, we contributed or discovered about a dozen molecular single gene causes of these disorders over many years. And I'm not going to bore you with all of the details, but one is particularly interesting. I'll just give you as an example of, and again, I won't even take you through this. Here's something called perilipin. It's a coordinator. This is the initiator lipase, the thing that comes onto the fat droplet and gives you energy when you're fasting. And it should, in the fed state, be off the droplet. And in the fasting, overnight, when you're starving, it should be on there, gobbling away and giving you the free fatty acid. And these people who have this specific mutation that kill off its interaction with this regulator, what happens to those people is that all day, even when they're eating, this regulator is pulling the lipase onto the surface of the droplet and driving free fatty acids into the body. And that alone is sufficient to cause every disease we're interested in the metabolic. So I'm aware of no other genetic defect and no other tissue that can do that. And this simple defect, just solely in the white fat droplet, is enough to cause every feature of the metabolic syndrome. To ask whether this was relevant for more common disease, you really these days have to go to big numbers, and that's when you have to deal with your epidemiological colleagues. And that's where I'm lucky to be in a group with fantastic epidemiologists, and we studied almost 250,000 people and found that if you look for people who are insulin resistant, had high triglycerides and low HDL, you found 53 variants in the genome that were strongly associated at a highly significant level with these phenotypes. And the key thing, much data, but I'm just going to pick out one highlight. Paradoxically, the individuals who have the highest score for being at risk of these metabolic diseases have less fat, not more fat. They have less fat particularly on the arms, on the legs, and in the gynoid area. So these genetic factors are actually like the lipodystrophies, meaning that, again, across populations, it's those individuals who are partially unable to make fat cells. So when you overnourish them, they behave a bit like the people with lipodystrophy. They don't have a safe place to put the fat because they cannot safely expand the fat depots on the buttocks and thighs. And they're the ones who run into real metabolic trouble. The apples, not the pears, if you like, in terms of the shape. And in very simple terms, we think of, think of a dodgy bathroom in a dodgy hotel with the bath plug gone and the taps left on, but you're all right, and they've even got carpet on the bathroom, imagine. But everything's fine because you get into steady state and you get a stored triglyceride. And we usually think about metabolic disease in terms of too much food in or not enough energy out. And that's what happens when you have that, too much in and not enough out, and you get a horrible soggy bathroom carpet and you get sick. But what we haven't really thought about enough is the fact that not everyone has the same size bath. so that a real determinant of the illness resulting from energy imbalance is the ability to store that excess of energy in a reservoir that is safe for us to use in the future. So can we take that even further? Well, we're trying to turn this from a philosophical construct into hard molecular entities that we can actually work on and maybe even develop drugs with. And here's just one final example. Here's a variant in a protein. This protein is highly expressed in adipose tissue. It's called ALK7. It's a signaling kinase. There is a variant that's present in 0.1% of the population. Those people are highly protected against developing diabetes if you carry that. Where is it? It's here. It disrupts the movement of this moiety out of the receptor. This is the key activation loop of its kinase. This is what binds the next protein down, SMAD3. When you when you have a threonine rather than an isoleucine, this can't move. So you can't do the signaling. And as we've shown in the lab, this is signaling dead. So, but the relevance of this then is that if you develop an inhibitor that would inhibit this in a safe way in humans, you might turn most wild-type humans who carry the regular, into those who are protected. So we might be able to use this information to create protective agents that make your, in other words, stabilize and safe and make your fat somewhat safer. So to end, I'm going to thank all the people who have helped me over my scientific life. They're enormous, and I really haven't had a chance to thank old mentors, Robert Turner in Oxford, Jeff Flyer in Boston, Nick Hales in Cambridge. I've been very, very lucky with my mentors over many, many years. But my colleagues in the IMS have been fantastic, including Sue Ozanne here, who's a member of the Rank Prize Committee. Sue is an old friend. In fact, Sue was one of the people who preceded me in Cambridge when I came in 1991. But particular thanks to two people that you may not know, but Chris Chatterjee and I were senior house officers together at the Hammersmith in 1984, and we followed each other around, and Chris has been my dear colleague in Cambridge for over 25 years, and he brings all the rigour and calm that I bring, the craziness and Sturm and Drang, and together we've worked, and we're continuing to work together, usually productively, in the area of nuclear receptors, and I've enjoyed it and still enjoy it all these days. And Nick, and my other colleague Nick Wareham, who co-directs the Institute of Metabolic Science with me, and bringing together epidemiology and public health medicine together with the sort of more focused molecular stuff that I do has been a real joy and pleasure. Thanks also to my family. Sadly, we're moving this week, so my wife is inundated with project management and is not here. But thank you all for inviting her and me, and thanks again for this great honour.